So our job in mechanics is to predict and explain motion. One of the ways of doing that is to try to coordinate between mathematical representations of the physics and more diagrammatic or graphical representations of the physics. In this video, what we're going to talk a little bit about is how we think about the momentum principle as it relates to force versus time graphs. So here I have the momentum principle, which governs all of motion. It allows us to make lots of predictions about how things are going to move. I've written it in this sort of change or derivative form that we talked about in one of the other screencasts. I want to move it around a little bit though. So I'm going to take this delta t to the other side, and I'm going to write it in sort of a more predictive way. That is that the change in the momentum is equal to the net force times the time interval over which the net force acts. And so you start to see here a way of making a prediction. We can decompose the change into the difference between two vectors. And we get a way of predicting the final momentum given the initial momentum plus the net force times the time interval. Okay? So this form right here is what we would call the update form of the momentum principle. It allows us to predict in the future what the momentum is going to be given what it is now and the net force that acts on the system. So a way to think about this in terms of the graphs is actually to look at this force versus time graph. Right? So if we take a time interval, let's say we take a delta t time interval here, and we look at that graph, it turns out that the area under this curve is the change in momentum for that time interval, because this is the product of the force times the time interval. This is precisely this calculation right here. We're just looking at it graphically. It's the area under the curve. You might see this when you think about the calculus way of writing this. So if we were to write the derivative form of the momentum principle times time, that's equal to the net force. If we were going to rewrite this into an integral equation, we would have this, which we would then integrate from some initial location or initial time to some final time. That's precisely what we're doing here, but we're doing it discretely. We're just saying there's some time interval over which the net force acts, and the area under this curve is precisely the change in the momentum. We can do that continuously, so we can go take another time interval. We can cut that up. And this is a new delta p. It's whatever the delta p is for this time interval with this net force acting. And we can continue to do that for each delta p. Now what you'll see is if we add up over the entire curve from here to here, the area under this entire curve is the total change in momentum that whatever object we're graphing here experiences. That's this whole graph, not just this blank part here, but the whole darn thing. That's the total change in momentum over this whole interval. So this is one way of thinking about how to coordinate between this more mathematical representation and a graphical representation of the same sort of thing.